Now let us take an example to understand how does this phase noise affect a receiver. Let's say we are trying to receive a signal centered around FRF, while at the same time there is also a blocker present at a frequency offset. Let's assume that frequency offset is around 10 megahertz. This is a blocker. This is the desired signal. And we want to down convert this signal with the help of an LO. Let's say this LO is at FIF lower than the FRF. So this is a heterodyne architecture. And this LO also has phase noise. Looking like this. So in the receiver, when we are going to multiply the LO signal with the signal which is coming out of the LNA, then we are going to filter out the high frequency components, so as to get components only around FIF in the baseband. So if we draw the spectrum at the baseband, and at around FIF we are going to get component due to the desired signal. But at the same time, since LO is having this side skirts because of phase noise, the received signal will also be having this side skirts. In addition to this desired signal, this blocker is also going to multiply with this LO signal, but its down converted component will appear at frequency different than the FIF. Since there is a 10 megahertz offset, so the blocker is going to also appear at 10 megahertz offset after mixing. But in addition to the blocker coming as it is, we also be having the side skirts because of the LO phase noise. This is phase noise. This one is LO phase noise. Down converted by blocker. We can see that even though this blocker may not be directly appearing at the FIF frequency, but because of this phase noise in the LO, so there will be some extra noise which will appear at the FIF because of this down conversion of the LO phase noise by the blocker. And this noise which is appearing at the FIF because of the blocker is going to degrade the SNR of the desired signal. So even though we can filter out the blocker, we can see that there is this component of the LO phase noise down converted by the blocker which is going to appear at FIF, as a result of which this is going to degrade the SNR of the desired signal. Megahertz, and you can see LO phase noise at 10 megahertz offset is scaled by blocker appears at this is going to be a problem, as there is no way to filter out this LO phase noise appearing at FIF due to blocker. This is also called as reciprocal mixing. This can be a serious problem if the blocker strength is very high in addition to phase noise present in the LO. So now let us try to understand how much of the LO phase noise we can tolerate for a given requirement. Say the channel bandwidth is 1 megahertz, implies the thermal noise floor at the antenna is going to be equal to minus 174 plus 10 log of 10 to the power 6, which is equal to minus 114 dBm. So if we don't want this LO phase noise which is appearing at FIF due to blocker to degrade the SNR, then we can just put a constraint that this noise coming due to reciprocal mixing to be at least 6 dB below the thermal noise floor. So the noise due to this reciprocal mixing should be P noise thermal minus 6 dB, which is coming out to be 120 dBm. So from this requirement on the noise due to reciprocal mixing, we can back calculate what should be the LO phase noise at 10 megahertz offset. So here assumption is that at 10 megahertz offset, this phase noise profile is going to be flat. So now we need to find out how much will be the noise at this 10 megahertz offset from the LO due to reciprocal mixing. So we will see that the ratio of blocker power to the noise at this 10 megahertz offset will be same as the ratio of LO power to the noise at 10 megahertz offset in the LO signal. And this ratio is what is given by the phase noise. So we will use the phase noise of the LO to find out what is the noise due to the reciprocal mixing. So we can write the phase noise due to reciprocal mixing in terms of blocker power and phase noise as P blocker plus the phase noise at given offset 10 megahertz integrated in the channel bandwidth. Now we are assuming that the phase noise at 10 megahertz offset is flat. So the integration will be just multiplication with the channel bandwidth, which is in our case 1 megahertz 10 to the power 6. Now let's say the given blocker power is equal to minus 30 dBm. Here we are also assumed that phase noise is flat at 10 megahertz offset. Now we can look at these two equations and find out what is the maximum phase noise which we can tolerate while making sure the reciprocal noise is 6 dB below the thermal noise floor. Is minus 120 dBm to be equal to minus 30 plus the phase noise plus 60 plus the phase noise at 10 megahertz offset to be equal to minus 120 plus 30 minus 60 equal to minus 150 dBc per hertz. So by this simple calculation, we can see that we can find out what should be the phase noise at a given offset so that the noise due to reciprocal mixing doesn't affect the overall SNR. Now here you will also note that so not only there is noise due to the reciprocal mixing, the desired signal itself down converts the phase noise of the LO. So we can see that this phase noise directly degrades the received SNR. In addition to that, this reciprocal mixing degrades it even further. The observation is that the phase noise degrades overall noise figure of the receiver and this happens in two ways. One way is the reciprocal mixing due to occur. The second is just the integrated phase noise in channel bandwidth can degrade the in-band SNR. But many times you'll find that this integrated phase noise within the channel is going to be much lower than the thermal noise floor, especially when the received signal is very weak. This is going to be much lower than thermal noise for received signal strength. This is what we have to be more concerned about.